In today's video, we'll be studying stereochemistry, and specifically we'll be studying stereoisomers. Here we have the outline of all we'll be studying in this video. We'll be studying the definition of stereoisomers or of isomers in general. We'll be studying the classification of isomers. We'll go on to study chirality, asymmetric centers and the difference between asymmetric centers and stereoisomers. We'll study isomers with one asymmetric centers. We'll learn how to draw enantiomers, naming of enantiomers with one asymmetric center. We'll take a look at perspective formula and Fischer's projection, optical activity, optical activity under which would consider specific rotation and enantiomeric excesses. Then we would go on to study isomers with more than one asymmetric center, after which we'll take a look at diastomers and meso compounds. So let's start off with our definition of isomers. Now, under our playlist, our organic chemistry playlist, Introduction to Organic Chemistry, we studied isomers and isomerism, and just as a review of what we studied in that video, we learned that isomers are compounds or molecules with the same molecular formula. Okay, so they have the same molecular formula, but they have different structural formula. Okay, so isomers are molecules or compounds that have the same molecular formula but different structure or different structural formula. But to be specific, they actually have different structure. Now, this structure could be in terms of connectivity. Okay, so the difference in structure could be in terms of connectivity, and it could be in terms of spatial arrangement. So how the atoms and how the groups are oriented in space, that is the spatial arrangement. Now, when the isomerism is in terms of different connectivity, what we have is a constitutional isomer. Okay, it's called a constitutional isomer when the difference in structure is based on different connectivity of the atoms in the molecule. So the molecules have the same molecular formula, but the atoms are connected differently in each of the isomer. Now, in terms of spatial arrangement, when we have molecules that have the same molecular formula but different spatial arrangement, what we have is a stereoisomer. And for this video, we'll be focusing on stereoisomers. Now, an example of a constitutional isomer would be, say for instance, let's take C2H6O. Okay, now this is the molecular formula C2H6O. From this molecular formula, we could decide to have an alcohol. Take for instance ethanol. So ethanol would be C. Okay, so we'd have a carbon, a hydrogen, a hydrogen here. We would have a carbon here, a hydrogen here, hydrogen again, and then would have oxygen and a hydrogen here. Now, if we count the number of hydrogens, we have 1, 2, 3, 4, 5, 6 hydrogen, which corresponds to our molecular formula. We have 1 oxygen and we have 2 carbons. Okay, now if we take a look at this structure, we would see that this is an ethanol. Okay, this is an ethanol. Now, this is a constitutional isomer for this molecular formula. Now, we could also decide to connect the atoms in a different way. So we could decide to have something that looks like this. We could decide to have the carbon here, and in between the carbons, we have an oxygen. Okay, now we attach our hydrogen atoms. So it looks something like this. Now, if we take a look at the molecule that we have right here, it still has the molecular formula C2H6O. However, this is not an alcohol, this is an ether. Okay, so this is dimethyl ether. Now, notice that these two molecules have the same molecular formula, but they differ in the connectivity of the atoms. While in this case, the oxygen is bonded to one carbon and one hydrogen, in this case, the oxygen is bonded to two carbons. Okay, so the connectivity differs, and this is basically what makes these two molecules to be constitutional isomers. Now, how about in a case where the connectivity could be the same, but these molecules only differ in the way their atoms are oriented in space? That's what we'll be focusing on in this video. So let's take a look at stereoisomers. Now, considering stereoisomers, there are two broad classification of stereoisomers. Okay, we have the conformational isomers, and then we have the configurational isomers. Now, for the conformational isomers could arise as a result of carbon-carbon single bond rotation or amine inversion. Now, for this video, we won't be focusing on these two types of isomers. Now, it's also important for us to take note of the fact that conformational isomers can interconvert randomly. Okay, so they cannot be separated. Interconversion from one form of conformational isomer, or conformers as they are called. Okay, so conformational isomers are called conformers. Now, interconversion from one conformer to another conformer does not require breakage of any bonds. Okay, so they can interconvert randomly. And we gave an example of the conformers that result as carbon-carbon single bond rotates. Okay, so take for instance we have ethene. Now, of course, as we stated earlier, we won't be considering conformational isomers in this video, but it's just as a brief overview. Let's take a look at how rotation about a carbon-carbon single bond can bring about different spatial arrangements. Remember that when we're considering stereoisomers, we're looking at the different spatial arrangements, how the atoms could be oriented in space. Now, if we take a look at the carbon that form this carbon-carbon single bond, they have an sp3 hybridization. Okay, so we also discussed some of this in our video on introduction to organic chemistry, so we won't be going over it again. So these carbon atoms have an sp3 hybridized orbital, and in terms of geometry, they have a tetrahedral orientation. Okay, so they look something like this in terms of orientation. Okay, a tetrahedral orientation. Now, what we have here, the ethene molecule represented here doesn't give us an idea of how the atoms are arranged in space. Remember that this molecule is a three-dimensional molecule, but we are representing it on a two-dimensional surface. Now, let's take a look at the ways in which this molecule could actually be oriented in three-dimensional space. So we have our ethene molecule. Okay, now basically a way in which conformational isomers are majorly represented is by means of the Newman projection. Okay, and under the Newman projection, there are two extremes of rotation about the carbon-carbon single bond. One extreme of rotation is the staggered conformation. So we have the staggered conformation, and another extreme of conformation or rotation is the eclipsed conformation. Now, the tetrahedral nature of this sp3 hybridized orbital is such that we would get to look at perspective formulas as we go on, but we could have a bond in the plane of the page, okay? We'd have a bond like this, and then another bond also in the plane of the page, and then a hatched or dashed wedge, and then a solid wedge. The solid wedge represents bonds that come out of the plane of the page, while the wedge represents bonds that go into the page. Okay, subsequently a video would be made that would be more in depth on the three-dimensional nature of molecules. However, just as a brief overview, for the staggered conformation, we have the atoms as far away as possible from each other. Okay, so the atoms of the two carbons that form the single bond are as far away from each other as possible. So we take a look at, so we'd have something like this basically. We would have a hydrogen here and a hydrogen here, hydrogen here. This is carbon 1. Okay, so looking at it from this view, okay, it appears as a dot, and because it eclipses the carbon behind, this carbon behind is represented as a bigger circle behind. Now the staggered conformation could look something like this. Okay, so here would have H, H, H. Now notice that this is a specific spatial arrangement. This is the staggered conformation. We could also have something that looks like this, which would be the eclipsed conformation, whereby the atoms that are bonded to the carbon are eclipsed. Okay, so they eclipse one another. So take for instance, we have our carbon 1, which we're representing as the dot here. Okay, and then we have a hydrogen here, hydrogen here, hydrogen, and now to the carbon 2, which is behind. The atoms bonded to the carbon 2 are eclipsed by the carbon bonded to the carbon 1. Okay, so we have something that looks like this. Now this is another conformation, the eclipsed conformation. Notice that as a result of rotation about the carbon-carbon single bond, there's able to be a change in spatial orientation of the bonded atoms. Okay, so we're talking about spatial arrangement or spatial orientation, and these two conformers are stereoisomers, because although they don't differ in connectivity, which if they differed in connectivity then they would be constitutional isomers, because they differ in terms of spatial arrangement, they are stereoisomers, and to be specific, they are conformational stereoisomers. Now of course, as I stated earlier, we're not considering this in details, and this is not a video on conformational isomers on human projection, but it's good for us to take note of that. Now coming back to our classification of stereoisomers, we also have the configurational isomers, which we'll be considering in this video. For the configurational isomers, there are two ways in which we could have configurational isomers. Okay, so we could have configurational isomers that are as a result of asymmetric centers, and those that are as a result of cis-trans orientation. Now for this video specifically, would be narrowing our focus to configurational isomers that arise as a result of asymmetric centers. Okay, but just as a touch into the cis-trans orientation, Also, when we made our video on introduction to organic chemistry, we spoke about the carbon-carbon double bond when we were dealing with alkenes. Okay, so the carbon atoms that form the alkene have this carbon-carbon double bond as a functional group. Okay, so we have the carbon-carbon double bond. Now, we learned when we were discussing alkenes that the nature of this carbon-carbon double bond is such that it prevents any form of rotation. Okay, so remember when we're talking about conformational isomers as a result of carbon-carbon single bond, we said that the carbon-carbon single bond allows for rotation rather, and since it allows for rotation, we could have different spatial arrangements. However, the carbon-carbon double bond prevents any form of rotation. So it means that if we have an atom oriented in this way, so we have an atom A oriented in this way, because the carbon-carbon double bond prevents rotation, this atom that is bonded in this direction is unable to change its spatial arrangement to a downward direction that looks somewhat like this. So an example would be, take for instance, we have something like this, and then here we have a hydrogen, we have hydrogen, here we have chlorine, and here we have chlorine. Take for instance, we have another molecule where we have a carbon-carbon double bond. On this side we have our chlorine, on this side we have our chlorine, and then we have the hydrogen here. Now notice that the orientation of the chlorine in this molecule, the molecule here, is in an opposite direction. So while the chlorine to the carbon 1 here is downwards, to carbon 2 here it's upwards. And because the double bond prevents rotation, the chlorine is unable to flip to the same side. So this molecule is unable to naturally or randomly transform to this, and this is unable to randomly transform to this. So it's important for us to take note of the fact that configurational isomers do not interconvert randomly. An interconversion from one form of a configurational isomer to another form of the configurational isomer involves breakage of bonds. So bonds would have to be broken in order for one form of the configurational isomer to be transformed to another form. Okay, so I hope we understand that. So this is a configurational isomer, the cis-trans isomer. So this has the cis orientation because the chlorine atoms are on the same side, and this has a trans orientation because they are on different sides. Okay, we won't be considering these types of isomers, but just as an overview, this is what the cis-trans isomer is about. So let's go directly into our focus of the day, which is asymmetric centers, configurational isomers that arise as a result of asymmetric centers. But before we do that, let's take a look at our outline. Now, considering our outline, so far we have been able to define isomers. We have seen the classification of isomers. Now let's take a look at chirality, which is our next subtopic for this video. Now, what exactly is chirality, and when is an object said to be chiral? Now, put very simply, a chiral object is an object which has a non-superimposable mirror image. Chiral object is an object that has a non-superimposable mirror image. Now, when we studied light, okay, so we didn't study light in this channel, but I hope that anyone watching the video has had prior knowledge in physics and chemistry, or probably biology. Now, when we study light in physics and we study about plane mirrors, we study about curved mirrors and how images are formed, we'd get to learn when we study plane mirrors and the characteristic of images formed by plane mirrors. Now, just to bring our minds back to our knowledge of physics, there are different characteristics of images formed by plane mirror. Would learn that one of them is that the image distance is the same as the object distance. Okay, so this is bringing us back to physics. Physics is coming to play here. So image distance is equal to object distance. Okay, would also learn that the image size is equal to the object size. So the magnification is equal to 1. The magnification is 1. Now, another very important characteristic of images formed by plane mirror, which would actually be considering in this video, is lateral inversion. Okay, now lateral inversion is a characteristic of images formed by plane mirror. Now, what exactly does this mean? If we have an image, okay, so take for instance, this is our image. We have our image like this, and then for our image, this is the left and this is the right. Now, lateral, or rather, this would be our object. Okay, so this is our object, and then this is our plane mirror. Now, what lateral inversion simply means is that the image produced by the plane mirror is going to change the position laterally. So the left of the object would become the right of the image. Okay, the left of the object would become the right of the image, and the right of the object will become the left of the image. So let's do that again. The left of the object would become the right of the image. So right here would have L, and then the right of the image, or rather the right of the object, would become the left of the image. Now, this is lateral inversion. This is basically what the mirror image, this is basically what the plane mirror does to an object. Lateral inversion. Left becomes right, right becomes left. This is lateral inversion. Now, what does it mean to superimpose? To superimpose means to lay over or to place over. Now, let's try to see if we can superimpose this image onto one another. Okay, so we have our object here, and then we have our image here. Let's try to superimpose them. Let's bring down our object, which has LR, and now let's bring our image, which has RL. Now notice that we can superimpose these two. This is the object and this is the image. We can't superimpose the image over the object because of the lateral inversion. Okay, because line over L would be R, and line over R would be L, so they can't be superimposed. However, in a case where we have something like this, on this side we have RR, and on this side, when it's placed in front of the mirror image would still give us an RR, because the left, okay, so this is the left, this is the right, the left would become the right, so this would be R, still an R, and the right would become the left, this would still be an R. If we bring our object and our image together, we have RR, and our image we have RR. Okay, so notice that these two can be superimposed. So an R would still lay over an R, and an R here would still lay over the R here. So they can be superimposed. Now, if you noticed, take note of the fact that this image, let's call this sample 2. Let's call this sample 2 or test 2. Sample 2, and this is sample 1. This is sample 1. Now notice that for sample 2, if we draw a line that divides our object into 2. So this is our object for sample 2. It's an R. If we draw a line that divides our object into 2 halves, okay, this is our line of symmetry. Now notice that the left half is identical to the right half. So there's a line of symmetry. The left is identical to the right, and so even when the mirror does the lateral inversion, because the left is identical to the right, when the left is switched with the right, it still remains the same. I don't know if we get the concept, but here we can see that there's a line of symmetry. The left is equal to the right, and so lateral inversion doesn't affect our object in sample 2. However, if we take a look at sample 1, let's bring down our object. So our object looks something like this. We have LR. Now if we draw a line that divides our object into 2, notice that this line of symmetry doesn't divide the object into 2 identical halves. Why is this so? On the left side we have an L, and on the right side we have an R. These 2 halves are not identical because we do not have the same letter of alphabet written on both sides. So when the mirror does the lateral inversion, it affects this object. So we can say in the sample 1 that the object here is asymmetric. It doesn't have symmetry because the one half is not identical with the other half. However, if we take a look at our object here, we can see that there is symmetry. In other words, this object here can be said to be symmetric. So we can see that there is a correlation between symmetry and chirality. So an asymmetric object is able to have a non-superimposable mirror image, while a symmetric object lacks that chirality. Okay, now another good way in which we can adequately view chirality is if we take our left hand and our right hand. Now, if we take a line of symmetry, okay, that divides the hands into left and right half. Okay, so this is a line here that divides the left hand, which is the object in this picture, into 2. Notice that the left half of this object is different from the right half of this object. On the left half of this object we have our thumb. On the right side of this object we have our little finger, our pinky. Now notice how the mirror does this lateral inversion. Okay, so the mirror converts the left, okay, the left side becomes the right side here. Okay, if we can see this, the left becomes the right and the right becomes the left. So a mirror image of the left hand is the right hand. Because there is no symmetry, these 2 image and object cannot be superimposed. So the left hand cannot be superimposed over the right hand because it's asymmetric. Okay, notice that if we try to superimpose it, the thumb doesn't lay directly over the thumb here. So the thumb in front this thumb doesn't lay over the thumb here. The pinky here doesn't lay over the pinky in the finger, in the hand behind. The hand behind has its pinky here, while the hand in front has its pinky here. So they are unable to be superimposed, and it's because of the asymmetric nature, because the left is not identical with the right. However, let's take a look at this flax that we have here. If we divide the flax into two equal halves, notice that the left side of the flax is identical with the right side of the flax. And so when the mirror does its lateral inversion such that the left becomes the right on this side, okay, so the left becomes the right on this side and the right becomes the left, notice that we still have identical images. Okay, the image is the same as the object because of that symmetry, because the left is identical with the right. That is the symmetry. And notice that they can be superimposed. The object flags can be superimposed over the image flags. Why? Because there is symmetry. So I hope we can see the direct relation between symmetry and chirality. Remember that a chiral object has a non-superimposable mirror image, and in order to have a non-superimposable mirror image, the object must be asymmetric. Okay, so this brings us to our next subtopic for the video. So I hope we are able to understand the concept of chirality. Now let's take a look at asymmetric center. What is an asymmetric center in chemistry? Now, because we're specifically considering organic chemistry, an asymmetric center would be, the asymmetric center would be considering is the carbon atom. So an asymmetric center is a carbon atom, or an atom in general, that is attached to 4 different groups. Okay, the carbon atom is, in order to be stable, must form at least 4 bonds. Okay, because the valency of the carbon atom is 4, so it must form at least 4 bonds. Now, in a case where the different groups attached to these 4 bonds are all different, so here we have A, here we have B, here we have C, we have D here. Now, notice that all of the groups are different. There is no identical group. Now, by the time we draw a line of symmetry, on the left hand side we have D, on the right hand side we have B. So it's asymmetric. There is no symmetry. The left and right halves are not identical. So that is an asymmetric center. The carbon atom is attached to 4 different groups. So let's take, for instance, this is attached to a methyl on this side, it's attached to a fluorine, it's attached on this side to a hydrogen, and on this side it's attached to a chlorine. Notice that all of the groups are different. Okay, the difference in these groups is what makes the carbon atom to be an asymmetric center. And being an asymmetric center, it means that it is chiral. The mirror image is unable to be superimposed. Okay, so let's try to get a mirror image of this object. Remember that the left, this is the left, this is the right. A mirror image is going to make the left of the object to be the right of the image, and the right of the object to be the left of the image. So a mirror image of this molecule would look something like this. So we'd have our carbon. On this side would have our methyl. It doesn't change because it's a lateral inversion. So it's only what lies laterally that would be inverted. Okay, this methyl group doesn't lie laterally, it lies superiorly. Okay, this lies inferiorly, and this chlorine and fluorine lie laterally. They lie on the side. Okay, lateral means on the side, and the plane mirror does a lateral inversion, not a superior inferior inversion. So atoms or the groups that lie superiorly and inferiorly remain in their original positions. However, the left is going to become the right. So we'd have fluorine on this side and would have chlorine on this side. Now notice that we can't superimpose these two images. We can't superimpose them. So an asymmetric center causes for chirality in a molecule. Now, what exactly is the difference between an asymmetric center and a stereocenter? Now, as we stated earlier, the asymmetric center is this carbon atom that is bonded to 4 different groups. Okay, so it's an asymmetric center. However, okay, a stereocenter is not necessarily always an asymmetric center. A stereocenter is simply an atom. It's an atom at which an interchange of 2 groups causes for a stereoisomer to be formed. I'll go over that again. A stereocenter is an atom at which if 2 groups are interchanged, a stereoisomer is formed. This simply means that a stereocenter could be an asymmetric center, or it could be an sp2 carbon atom. Now let's take a look at this. In the example we considered earlier, we had CH3, we had chlorine, we had fluorine, and then we had here hydrogen. Now we said a stereocenter is an atom at which if 2 groups are interchanged, it leads to the formation of a stereoisomer. Now a stereoisomer or stereoisomers have different spatial arrangements. Now so far we have been discussing stereoisomers, and we have been looking at them as 2-dimensional molecules. They are actually 3-dimensional molecules, but for simplicity, until we get to perspective and Fischer's projection, they would be presented like this for now. But it's important for us to take note of the fact that they are actually 3-dimensional molecules. Now back to the stereocenter. This carbon atom is an asymmetric center. Why? Because it's attached to 4 different groups. But it's also a stereocenter because if we interchange 2 groups that are attached to this carbon atom, it would give us another stereoisomer. Now let's take a look at this. If we interchange fluorine with chlorine, so basically chlorine takes the position of fluorine and vice versa. So CH3, okay, chlorine, fluorine takes the position of chlorine and vice versa. Now notice that this is another stereoisomer, although it doesn't look like it because we're not looking at it as a 3-dimensional structure. But when we consider perspective drawings or perspective formulas, we would see it more clearly that this figure A and figure B are different stereoisomers. Okay, so the carbon in this molecule is both an asymmetric center in that it's attached to 4 different groups, and it's a stereocenter in that when 2 groups that are attached to the carbon are interchanged, it gives us another stereoisomer. And for simplicity, I didn't interchange methyl with hydrogen because it won't be so clear for us to see that they are actually stereoisomers because of the 2-dimensional way in which I have been representing these structures. However, an interchange of methyl and chlorine, or rather of methyl and chlorine, fluorine and methyl, any interchange of 2 groups would give a stereoisomer. Okay, we'll get to see more of this as we go on. Now, as I said earlier, the stereocenter could also be an sp2 carbon. Okay, so pick for instance, we have this sp2 carbons, okay, and we have an attachment here, we have an attachment here in order to form 4 bonds, and then we also have an attachment here and an attachment here. Now we have here hydrogen, and we have here chlorine. We have here hydrogen, and we have here chlorine. Now when we were studying this, we said this is a cis-trans stereoisomer. Why? Because the double bond prevents rotation, and so the spatial arrangement remains the same. However, notice that if we interchange these two, okay, so if we interchange these two, we'd have something that looks like this. We'd have hydrogen here bonded to the carbon. On this side would have chlorine, on this side would have chlorine, and on this side would have hydrogen. Notice that as a result of interchanging two groups, we have been able to form a different stereoisomer, which is the trans stereoisomer. So although this carbon atom is not an asymmetric center. Why? It's not an asymmetric center because it's not bonded to 4 different groups. It's only bonded to 3 different groups. It's bonded to a hydrogen, it's bonded to a chlorine, and it's bonded to a carbon. 3 and not 4, but an asymmetric center ought to be bonded to 4 different groups, but it's bonded to 3 different groups. However, it's a stereocenter because when we interchange 2 groups that are bonded to the carbon, it leads to the formation of a stereoisomer. So by the time we interchange, okay, we have a conversion from a cis isomer here to a trans isomer here. So this is the relationship between an asymmetric center and a stereocenter. Okay, so I hope we get the idea of asymmetric center and stereocenter. Some texts use the two terms interchangeably, but they are actually different. So we can see by now that all stereocenters, okay, or rather all asymmetric centers are stereocenters, okay, but not all stereocenters are asymmetric. Going over it again, all asymmetric centers are stereocenters, but not all stereocenters are asymmetric centers. So it's important for us to take note of that. So let's go back to our outline. Alright, so going by our outline, let's take a look at isomers with one asymmetric center. The isomer would be considering for this video is 2-bromobutane. Okay, so let's consider 2-bromobutane. First, we'll start off by drawing out the structure. However, here we can see that the asymmetric center is asterisk, and we can see that it's the second carbon. Okay, so let's draw it out. We have a methyl on this side, then we have our asymmetric center. It's bonded to a hydrogen. We have a bromine here, and then we have our ethyl group right here. Okay, this is our asymmetric center drawn as a 2-dimensional structure. Now, so far we have been considering our molecules as 2-dimensional structures, but before we go on in our study, it's important for us to take note of the perspective formula. Okay, for this video we'll be making use of the perspective formula as well as the Fischer's projection in representing 3-dimensional molecules. Now, the perspective formulas makes use of wedges. Okay, we have the dashed wedge, which is sometimes called the hatched wedge. Okay, dashed or hatched wedge, and then we have solid lines. Alright, now let's take a look at this. In drawing a perspective formula, we have a asymmetric center, okay? The carbon, which is the asymmetric center. Now we have our solid lines. The solid lines represent bonds that are in the plane of the two-dimensional surface. Now the two-dimensional surface that we're working with is a paper, okay, or a screen as we have it here. So the bonds that are represented as solid lines are bonds that lie in the plane of the paper or the two-dimensional surface. Now we have a dashed wedge. Okay, the dashed wedge represents bonds that go into the paper or into the two-dimensional surface, pointing away from the viewer. Okay, that is the dashed wedge. And then the solid wedge represents bonds that come out of the paper towards the viewer. Now, in drawing a perspective formula, it's important for us to take note of the fact that the two solid lines must be adjacent to each other. So we cannot draw a wedge in between the two solid lines. This perspective formula would be wrong. Okay? Also, the two wedges must be adjacent to each other. Okay? We cannot draw a solid line in between the wedge such that they are not adjacent. Okay, it's important for us to take note of that. Another important thing for us to take note of is the fact that in drawing a perspective formula, the dashed wedge would usually be above the solid wedge. Okay, so it's important for us to take note of these key points in drawing a perspective formula. So it's used for drawing a three-dimensional molecule onto a two-dimensional surface as we have it here. Now back to our molecule of discussion, which is 2-bromobutane. Okay, so we have it here, 2-bromobutane. Okay, and we drew it earlier as we have our methyl group here, we have our carbon, we have hydrogen here, we have the bromine, and here we have ethyl. Now, how do we draw this onto a two-dimensional surface, representing this three-dimensional molecule on a two-dimensional surface? Now, in drawing this molecule, we could arrange or orient the groups in any fashion. Okay, we could orient the group anyhow we want to. So I could decide to attach here. I would attach here my bromine. Okay, I would attach bromine here, and then I would attach ethyl on this side. I would attach here hydrogen to the hatched or dashed wedge, and I would attach here methyl. Okay, this is the orientation I've decided for this particular molecule. Now, how do I get the mirror image of this molecule? Okay, how do I get the mirror image? Now, remember when we were studying about the difference between asymmetric centers and stereocenters? Okay, we said that all asymmetric centers are stereocenters, but not all stereocenters are asymmetric centers. And we define an asymmetric center as an atom at which if two groups are interchanged, it leads to the formation of another stereoisomer. So given this carbon, given an asymmetric center to be a stereocenter, it means that if we interchange two groups that are attached to this carbon, would be able to get another stereoisomer, and this other stereoisomer is the mirror image. Okay, how do we know it's the mirror image? We know it's the mirror image because this particular molecule has only one chiral center. Okay, and since it has just one chiral center, a stereoisomer that is different from this molecule is definitely going to be its mirror image. However, if it happens to have multiple chiral centers and multiple asymmetric centers, we could have stereoisomers of that molecule that are not necessarily enantiomers. We'll get to see this when we consider diastemers, okay? But for now, any interchange of two groups would lead to the formation of the mirror image or the enantiomer of this molecule. So let's interchange two groups, okay? So we decide to interchange ethyl and methyl, okay? So we have here interchanging methyl and ethyl, would have bromine here. Right here would have a methyl, and then on the solid wedge, which is here, would now have a ethyl CH2 CH3, and now on the hatched or dashed wedge would have a hydrogen. So this molecule is a stereoisomer. It's an enantiomer of the molecule above. Okay, it's good for us to take note of that. Now, having been given these two structures, okay, the name for these two structure A and structure B. Structure A and structure B both have the name 2-bromobutane. So how exactly are we able to differentiate? So when I say 2-bromobutane, how do you get to know whether I'm referring to the structure A or the structure B? This brings us to the system of nomenclature. It is the Ingold-Prelog system. Ingold-Prelog system. Now, how exactly does this system work, and what is the basis of the nomenclature? Now, the enantiomers are given the configuration R or the configuration S, depending on the orientation of groups about the asymmetric center. Okay, they are either given the configuration R or the configuration S. Now, what determines the orientation is basically the priority of the groups. Okay, so we have group priority. Now, in determining what group has a higher priority, we make use of the atomic number of such a group. So the group that is directly attached to the asymmetric center, to be specific, the atom that is directly attached to the asymmetric center, we consider the atomic number of that atom, and through the atomic number, comparing it with the atomic numbers of the different other atoms that are attached, we're able to determine the orientation or the configuration, whether it's an R or whether it's an S. Now let's visualize this. So take for instance, this is our asymmetric center, okay, and we have a solid line, we have a solid line here, we have a dashed wedge, and we have here a solid wedge. Now attached here is A, attached here is B, attached here is C, and attached here is D. Okay, now considering this, okay, let's take it such that the priority depends on what letter of the alphabet comes first. Okay, now A comes first, the letter A comes first, so it has priority number 1. Okay, now remember that when we're considering actual molecules, we're considering the atomic number. Okay, so A has the number 1 priority. Okay, B has the number 2 priority, C has the number 3 priority, and D has the number 4 priority. Now, how exactly do we determine whether this particular molecule has an R configuration or an S configuration? Now, an R configuration would be a molecule whereby drawing an arc, okay, drawing an arc from 1 to 2 to 3 gives us a clockwise direction, or it runs to the right. Now, the R, this R notation that we have here stands for rectus, which is right in Latin. Now, however, it would have the S configuration if moving from 1 to 2 to 3, we move in an anti-clockwise direction. Okay, anti-clockwise. Now S here is Latin for sinister. Sinister means left. Okay, now it's important for us to take note of the fact that this holds, okay, this configuration holds when the least priority group is attached to the dashed wedge. Emphasis on this. The least priority group must be attached to the dashed wedge. So this condition holds when this is the case. If we are able to move from 1 to 2 to 3 in a clockwise direction, then it's an R configuration as long as the least priority group, which is the fourth priority group, is attached to a dashed wedge. And it's an S configuration if we're able to move from 1 to 2 to 3 in an anti-clockwise direction so far the least priority group is attached to a dashed wedge. Now in this example given here on the screen, we can see that our least priority group is a D, and D is attached to a dashed wedge. So we can go on with this condition. Now let's move from 1 to 2 to 3. Okay, now if it so happens that we have to move from 1 to 4 to 2 to 3, we simply assume that 4 doesn't exist. So as long as we move from 1 to 2 to 3 and not the other way around, this condition still holds. So let's move from 1, 2 to 3. Notice that we move in a clockwise direction. Okay, this is a clockwise direction, and because the least priority group is attached to the dashed wedge, this has an R configuration. Okay, so if I give a molecule and the molecule is a C A B C D, okay, for instance CABCD, which would be the molecular formula for the molecule on the screen, having been told that the orientation is R, I won't go about drawing any random three-dimensional structure. So let's check this out. Very interesting. So now I'm not giving the structure, I'm giving the molecular formula. Okay, I'm giving the molecular formula and I'm told that it's an A B C D C, okay, which is what we have here, A B C D C, or rather AC, well anyway, A B C D C, these are the constituent molecules in quotes in our compound. Okay, and I'm told that this has an R configuration. Okay, this has an R configuration, and it so happens that we know that C is the asymmetric center. So let's keep that in mind. We know that C is the asymmetric center. Now let's take a look at this, because we'll be able to tell from the configuration how to draw the structure. Okay, so we'd have C as our asymmetric center. Okay, now we can draw our bonds around C. So the dashed wedge, the solid wedge, the dashed wedge here. So sorry, it doesn't look so neat. So now, how exactly are we able to go from the molecular formula giving the orientation to the structural formula? Now take a look at this. We attach our least priority group to the dashed wedge. So our least priority group is D. Okay, now attach the highest priority group to anywhere on the molecule. I decide to attach the highest priority group here. Okay, so I have A there. Now I know that for an R configuration I have to move in a clockwise direction from the highest priority group. Alright, so we have decided to attach our highest priority group to a solid line, and we know that for an R configuration we need to move from the highest priority group to the third group in a clockwise direction. So now we'll draw an arc that runs in the clockwise direction. Okay, So it means that this has to be a 2 and this has to be a 3. So here we would attach B, and then we can attach here C. So we can see that from the molecular formula, given the orientation, we are able to determine which of the molecule we're actually referring to. Now let's go back to our molecule of interest right here. Now let's determine the configuration of the first molecule. Okay, the configuration of the first molecule. Now remember, in considering our priority, we're going to make use of the atomic number. Now, considering the groups that are directly attached to the asymmetric center, okay, right here we have bromine directly attached to the asymmetric center. So we have bromine. Right here we have carbon directly attached to the asymmetric center here. Right here we have another carbon, so we have carbon, and here we have hydrogen. Now, without doubt, we know that hydrogen is the atom in the periodic table with the least atomic number. Since it has the least atomic number, it means that it would have the least priority. So we'd assign hydrogen with priority number 4, indicated here, priority number 4. Now, coming to bromine, comparing bromine and carbon, these two carbons, we know bromine has a higher priority number, okay, or rather has a higher atomic number than carbon. So bromine would definitely take number 1, okay, it would take priority number 1. Now carbon and carbon, which are directly attached to the asymmetric center, tie. Okay, so there's a tie because they have the same atomic number. Now, how exactly are we able to break this tie? We break this tie by considering the atoms that are directly attached to these atoms. Okay, so directly attached to this carbon is a hydrogen. So we have 2 hydrogens and a carbon directly attached to this carbon. Now directly attached to this carbon we have hydrogen, hydrogen, and hydrogen. Now let's try to break the tie. Comparing carbon and hydrogen, we can see that carbon of course has a higher priority. So this carbon would have the higher priority, and this is 2. And then of course this carbon that is attached to hydrogen, hydrogen, hydrogen would be the 3rd place in terms of priority. Now let's check if our condition is right. Okay, now notice that the least priority group, which is hydrogen, is attached to the dashed wedge. So we can go ahead to draw a line that goes from 1, 2, 3 and check if it's clockwise or anti-clockwise. So let's do that. Now 1, 2, 3. Okay, we can see that our arc goes in a clockwise direction, and since it goes in a clockwise direction, this has an R configuration. So this has an R configuration. So in naming this particular molecule, it would have the name R2-bromobutane. Okay, to be specific about the particular 3-dimensional structure of 2-bromobutane that we are considering, it's the R configuration. Okay, now it's important for us to take note of that. Now let's go down here and consider the second molecule, which we already established is a mirror image. And remember why we said it's a mirror image? We said the asymmetric center is a stereocenter. And being a stereocenter, if we're able to interchange 2 groups, then we're able to form a stereoisomer. And we said since it's just one asymmetric center, that particular stereoisomer is an enantiomer. It's a mirror image of our structure. Okay, so now let's take a look at this. We interchanged methyl and ethyl. Okay, now we already have our priority groups. So this is priority number 1, this is priority number 3 and this is priority number 2. Now take note of the fact that our least priority group, which is priority number 4, is attached to a dashed wedge. Okay, very important. It's attached to a dashed wedge. So it means that we can go ahead to draw a line from 1 to 2 to 3. Now, if we move in this direction, we'd be going from 1 to 3 to 2. So we'd have to move in this direction, acting as though the 4 doesn't exist there. It doesn't matter if we pass through priority number 4, as long as we go from 1 to 2 to 3. Okay, now notice that we go in an anti-clockwise direction. So this has an S configuration. Very interesting. This has an S configuration. So this is S2 bromobutane. Okay, so we can see our two mirror images. Now, aside interchanging two groups, we could actually form a stereoisomer by flipping, making a lateral inversion to our molecule such that the left becomes the right and the right becomes the left. So let's take a look at that. Okay, let's laterally invert this molecule. A lateral inversion of this molecule would look something like this. Okay, would have our carbon as the asymmetric center. Right here would have bromine, would still remain in its original position. However, the left hand side would become the right hand side. So right here would have a dashed wedge with hydrogen. We would have a solid wedge right here with methyl. Now this is our plane mirror. Okay, plane mirror for the lateral inversion. And right here on the solid adjacent line would have our ethyl group. Okay, so this is CH2CH3. Okay, this is the ethyl group. Now notice that this is a mirror image of this structure. Okay, this is a mirror image of this structure. So it means that this structure ought to have the same configuration as this structure, since they are both mirror images and there's only one asymmetric center. Okay, so let's check out the configuration of this structure. This has priority number 1, this has priority number 2 as we saw earlier, this has priority number 3, and this has priority number 4. Now in going from 1 to 2 to 3, let's check that out. So this is the direction from 1 to 2 to 3. So 1 to 2 to 3. Notice that we move in an anti-clockwise direction. Okay, so this has an S configuration, also because our least priority group is attached to the dashed wedge. That is very important. The least priority group doesn't have to be hydrogen. It could be another atom, but always take note of the fact that in order for us to take clockwise to be R and anti-clockwise to be S, the least priority group must be attached to the dash wedge. So in this structure that we have here, the least priority group is attached to the dash wedge, and we move in an anti-clockwise direction, so it's an S. Okay, now notice that these two molecules have the same configuration, however they have different perspective drawings. Okay, they have different perspective drawings. Notice that here bromine is attached to the solid line, yes. Methyl is attached here to a solid wedge. Methyl here is attached to a solid line. Ethyl here is attached to a solid wedge. Ethyl here is attached to a solid line. Okay, so it's important for us to take note of the fact that a particular molecule could be represented by two or more different perspective formulas, but in determining whether the perspective formulas are the same, what we need to do is to take note of the orientation, and we use the can-angle prelog system, okay, to take note of that orientation with the perspective drawing. Now, so far we have been considering when the least priority group is attached to the dashed wedge. How about a situation where the least priority group is not attached to the dashed wedge? Now let's take a look at that. Okay, so we'd still be working with our molecule, which is 2-bromobutane. Okay, 2-bromobutane. Now we'll draw a structure that looks like this. This is our dashed wedge, and then this is our solid wedge. Now I would attach here ethyl, I would attach here bromine, I would attach here hydrogen, and I would attach here methyl. Okay, we're still working with 2-bromobutane, and these are the attached groups. 4 different groups is an asymmetric center. Our carbon is an asymmetric center. This carbon right here is an asymmetric center. Now take note of the fact that in this particular molecule, the least priority, which we already determined to be hydrogen, is not attached to the dashed wedge. So how exactly do we go about this? We have to interchange 2 groups such that hydrogen would now be attached to the dashed wedge. Okay, now take note of the group attached to the dashed wedge. The group attached to the dashed wedge is bromine. So we're going to interchange bromine and hydrogen. So we'd have something that looks like this. We'd have our ethyl here as usual. We would have bromine, would now take the place of hydrogen. Would have our solid wedge, looks something like this, with methyl here. And then on our dashed wedge, hydrogen has taken the place of bromine. Now notice something very carefully. Notice that we have interchanged 2 groups about the asymmetric center. Now what does that mean? Because the asymmetric center is a stereocenter and we have interchanged 2 groups, it means that we have a different stereoisomer. So this molecule here in red is a stereoisomer of the molecule here in white. Okay, they are stereoisomers and it's just one asymmetric center. So let's take a look at this. Now in numbering in terms of priority, this of course we determine to be 1, we determine this to be 2, and we determine this to be 3, and of course 4, least priority group. Now let's go from 1 to 2 to 3. So this is from 1 to 2 and then to 3. Okay, notice that we're going in an anti-clockwise direction, and an anti-clockwise direction is an S. But that configuration is for this molecule, not for this molecule which we started with. The configuration S is for the molecule in red, not for the molecule in white. Now how exactly do we determine the configuration for the molecule in white? We know that the molecule in red is a mirror image of the molecule in white. So if the molecule in red has an S configuration, then the starting molecule would definitely have an R configuration. So this we know now has an R configuration. Okay, so whenever the molecule is attached in this way, such that the least priority group is not attached to the dashed wedge, we interchange 2 groups such that the least priority group becomes attached to the dashed wedge, and after doing that we find the priority, or we find the configuration of our new molecule. The reverse configuration of the new molecule is the actual configuration of our starting molecule. I hope we're able to understand it. Now coming back here, okay, remember we started from our original molecule in white. We interchanged 2 groups, bromine and hydrogen, and we're able to form our molecule in red. Now take note of this, very interesting. When we interchange two groups, we form a stereoisomer of the original molecule. So let's call this the original. This is the original, and let's call this the duplicate in quotes. Okay, the duplicate in quotes. So we have original and duplicate, but that's just for understanding purposes. So we interchanged two groups and we formed the duplicate. Now, given the duplicate, if we interchange another two groups, we're going to form the original. This is very interesting. Now, let's take a look at that. Okay, so we have our duplicate, right? Let's interchange another two groups, and we'll see that the molecule formed by interchanging another two groups in the duplicate would lead us back to the original. Very interesting. Okay, so this is it. Let's interchange two groups at random. Okay, so I wouldn't want us to tamper with the least priority group on the dash wedge, so we don't have to go through all of that route again. Let's keep the least priority group on the dash wedge and interchange any two groups of your choice. Okay, but do that just once. So I'll decide to interchange bromine and methyl. Okay, so let's take a look at that. Ethyl would remain in its original position. Okay, so ethyl would remain in its original position. Right here, I have decided to interchange bromine and methyl. So right here, I would have methyl. On the solid wedge, right here, I would have bromine. And on my dashed wedge, I still have a hydrogen. So this new molecule is a double interchange of the original. Okay, I hope we're following in the concept. So now we have this new molecule, and I'm making a prediction that this new molecule that we have formed is actually our original molecule because we have interchanged twice. Now let's check out the orientation, and I'm predicting that the orientation is an R. So let's check that out. Now priority number 1, let's give this the bromine is priority number 1, ethyl is priority number 2, methyl is priority number 3, and hydrogen, of course, is priority number 4. Now let's move from 1 to 2 to 3. So we're going to go in this direction. Notice that we went in a clockwise direction. We went in this direction. Let's do that again. Okay, so we went in this direction. This is our direction, a clockwise direction. And since our priority group, our least priority group, is attached to a dashed wedge, and we're going in a clockwise direction, this has an R configuration, as I predicted. Very interesting. So we're back to our original molecule. Very interesting. Okay, so this is important for us to take note of. If we interchange two groups, we form a stereoisomer. But provided that the molecule has just one asymmetric center, if we interchange again any two groups, we actually go back to the original molecule. Okay, so that's very interesting. Another very interesting thing for us to take note of is that if we interchange two groups, we form the stereoisomer. Okay, if we make a mirror image of the stereoisomer, we go back to our original molecule. Now let's take a look at that. Okay, let's take a look at that. So this is our duplicate. Okay, we formed this duplicate by interchanging two groups from the original. Now we want to form a mirror image of the duplicate, and this is just to show us that the mirror image of the duplicate will take us back to the original. Now let's check that out. So lateral inversion, of course, left becomes right, right becomes left. Okay, so we'd have something that looks like this. We'd have ethyl here retaining its original position. On this side, lateral inversion, so we're going to have our wedges on this side. Okay, would have methyl on this side, and then bromine would now be on this side. This is a mirror image of this structure, the duplicate. Now let's take our priorities. 1, this priority 2, this is priority 4, and this is priority 3. Now let's go from 1 to 2 to 3. Okay, from 1 to 2 to 3. We're going to move in this direction. Now notice that this is a clockwise direction. Okay, it's a clockwise direction. Being a clockwise direction, our least priority group is also attached to the dashed wedge. So this has an R configuration, same as our original molecule. So there are two ways in which you can go from a molecule to its stereoisomer. You can do that in two ways. The first way to go from a molecule to its stereoisomer is simply by lateral inversion. That's how the mirror image is formed, lateral inversion. And a simple way of performing lateral inversion of on a plain sheet of paper with the perspective drawing, let the left become the right and the right become the left. That's the lateral inversion. When you perform the lateral inversion on a molecule, you form its mirror image. Okay, so you're forming another stereoisomer. The other way is to interchange any two groups once. Do this once. Interchange two groups once. If you interchange two groups and you laterally invert, you're going back to the starting point. Okay, so if you laterally invert and interchange two groups, you're going to the starting point. If you laterally invert twice, you're going back to the starting point. If you interchange two groups twice, you're going back to the starting point. Very interesting. Okay, so I hope we're able to understand this concept. So that is how stereoisomers are named. Okay, as we'd actually go on to see or go on to study some practice questions so we could better understand the entire concept. So let's go back to our outline. Now, going by our outline, we've been able to draw the enantiomer. We've also been able to consider isomers with one asymmetric center and how to draw enantiomers. Now, of course, we'd later on consider perspective formula and Fischer's projection, but we've considered how to draw enantiomers and also how to name the enantiomers. Okay, so we simply represent the configuration in a bracket and name the molecule as usual. Okay, very interesting. Now let's go on to check out the perspective formula. We've already considered perspective formula, so we'll be considering Fischer's projection. Okay, very quickly. Now, the Fischer's projection is another way of representing three-dimensional molecules on a two-dimensional surface, but it's a little bit different from the perspective formula. So let's check this out. In a Fischer's projection, the intersection of two perpendicular lines, okay, so the intersection that we have right here, which I just circled, is an asymmetric center. So an asymmetric center is represented by the intersection of two perpendicular lines. Okay, that is an asymmetric center. Now, it's also important for us to take note of the fact that in a Fischer's projection, a horizontal line represents a solid wedge. Okay, horizontal line, solid wedge. And a vertical line represents a dashed wedge. Dashed wedge. So now let's draw a Fischer's projection of bromobutane. Okay, of 2-bromobutane. Now, just as we did when we were drawing our perspective formula, just take out the basics of the projection. An intersection represents an asymmetric center. For this particular molecule, we have only one asymmetric center. Okay, only one asymmetric center. Now, just before we go further, To avoid confusions when performing lateral inversion, it's better to interchange two groups. Okay, so if you're trying to form a mirror image of a particular molecule with one asymmetric center, rather than trying so hard to laterally invert and making a mistake in the process, it's safer to simply interchange two groups once. Interchanging two group once would lead to the formation of the mirror image. So that's just to clear any doubt when trying to laterally invert. But do not laterally invert and interchange two groups at the same time. If not, you're counteracting the effect. Interchanging two group counteracts the effect of lateral inversion and vice versa. So you'd be going back to the starting point. I hope it's clear. So we have our molecule here, 2-bromobutane, and we're trying to represent it in a Fischer's projection. Okay, so we said that the intersection of two lines represents an asymmetric center. We have only one asymmetric center in this molecule, so we would only be representing it with one intersection. So we'd have only one intersection in a Fischer's projection. Okay, now this is our symmetric center. We can decide to attach here a hydrogen, whatever we like. We could decide to attach a hydrogen here. Let's decide to attach a bromine here. We could decide to attach a methyl here, and then attach our ethyl here, CH2, CH3. Okay, now this is very interesting. We need to pay attention here. Lateral inversion for the Fischer's projection is very direct, okay, because here we can actually see structures that lie laterally and we could actually invert them. The drawing of a perspective formula may not necessarily represent structures that lie laterally, so the lateral inversion is not always so reliable. But for the Fischer's projection, the lateral structures are actually represented very clearly. So here on this side, we know for sure, very certain, that hydrogen lies on the left. It's not our eyes deceiving us, it actually lies on the left. Okay, so lateral inversion is very straightforward and there's likely to be no error. Okay, so we could simply form a mirror image of this structure very directly. Okay, now coming back to our structure here, we have this orientation. Okay, we have decided this random orientation for our structure, but we do not know whether this is an R2-bromobutane or an S2-bromobutane. So how do we get to determine that? Now, as usual, take your priorities. So this is priority number 1. This, as we determined earlier, priority number 3. This is priority number 2, and then this is priority number 4. Now this is very interesting. Notice that hydrogen is attached to a horizontal line. Okay, and we stated earlier that a horizontal line in a Fischer's projection represents a solid wedge. Now in this particular molecule, hydrogen happens to be the atom with the least priority group. Okay, and for us to take our configuration to be what it is, the least priority group must be attached to a dashed wedge. So what do we do at this point? Let's take our configuration. Okay, so let's go from a 1 to a 2 to a 3. So 1 to 2 to 3. Notice that we are going in an anti-clockwise direction. So this is an S, but not too quick. Okay, not too quick, because our least priority group is attached to a horizontal line. In other words, it's attached to a solid wedge. But in order for this to be an S, it has to be attached to a vertical line which represents a dashed wedge. Now, our least priority group is attached to a horizontal line. That is a solid wedge. With our least priority group on the solid wedge, which is a horizontal line, we took our direction from 1 to 2 to 3, and it's an S. Now, because the least priority group is attached to this solid wedge, which is a horizontal line, the actual configuration of this molecule is the reverse configuration. So it's an R. So this molecule has an R configuration. Why? Why not an S configuration? Well, because the least priority group is attached to a solid wedge. Okay? And it ought to be attached to a dashed wedge in order for us to maintain the S. I hope we are able to understand it. Okay? Now, let's take a mirror image of this molecule. Okay, so a mirror image lateral inversion. It's very straightforward for the Fischer's projection. Left becomes right, right becomes left. The molecules or the groups that get attached to the vertical lines are not affected by the lateral inversion. Because remember, as I stated earlier, it's a lateral inversion. So it only affects structures that lie laterally. Okay, the structures that lie on the top or on the bottom or superiorly and inferiorly are not affected. Okay, now so bromine will remain in its original position, ethyl would remain in its original position. However, the left becomes the right and the right becomes the left. So this is the left here, this is the right here. So the left becomes the right, this is the right here. So hydrogen would take the right. Okay, and the right becomes the left. So methyl would come here to become the left. Okay, taking our priorities, this is priority number 1, this is priority number 3, this is priority number 2, and then this is priority number 4. So let's go from 1 to 2 to 3. Going from 1 to 2 to 3, we have 4 intervening, but would act as if it's not there, and then would go from 1 to 2 to 3. Notice that we are going in a clockwise direction. So it appears as if this has an R configuration. But remember, our least priority group is attached to a horizontal line which represents a solid wedge. So what do? We reverse the configuration. So although this seems like an R, it's actually an S. Now let's go back to our outline. Now going back to our outline, we have considered the perspective formula. Now let's take a look at optical activity. Going back to physics, we're going back to our study of waves. Now when we studied waves in physics, we learned that we have longitudinal waves. I hope we can still remember. We learned that we had longitudinal waves and we learned that we had transverse waves. Very interesting. We learned that waves have all of these very interesting properties. They have properties like reflection, refraction, diffraction, and so on. But we were taught a particular thing, and we were taught that a singular characteristic of transverse wave that is not exhibited by longitudinal waves is the fact that transverse waves can be polarized. Okay, so transverse waves can be polarized. Now, light is a transverse wave. Okay, so this means light can be polarized. Now, when we have light coming from a natural source, so this maybe could be the sun, and then we have light coming from this source. We have different rays of light coming from this source, and we have the collection of these rays forming beams. Now it's important for us to take note of the fact that when light comes from a natural source, the rays of light oscillate in different directions in space. So we have some rays of light oscillating in this direction vertically. We have some waves orienting in the horizontal axis. We have some moving at various angles and inclinations. They oscillate in different directions in space. Okay, this is an unpolarized light. So this light is unpolarized. Now when this light is made to pass through a polarizer, okay, so Take for instance, this is a polarizer P, and so we make this light pass through the polarizer. Now this polarizer acts as a filter, and it filters based on its axis of polarization. So we have what we call the axis of polarization. Different polarizers have different axes of polarization. But let's take for instance that the axis of polarization of this particular polarizer is in the vertical axis. Okay? It means that this polarizer is going to filter out every ray of oscillation that is not in the vertical axis. So this polarizer is going to be a filter. So if you, as a ray of light coming in the horizontal direction, it blocks you out. You're coming at an angle of 60 degrees, it blocks you out. But you're coming in the vertical direction, you're free to go. Okay, so the polarizer acts as a filter, and so at the end of the day we have all of these rays of light that are vertically oriented. This light emanates as a polarized light. Okay, of course this video is not centered on light and the properties of light, but just for the basic understanding of what polarization does, this is exactly what it does. It acts as a filter based on the axis of polarization. Now, what exactly is optical activity, and why are we bringing physics into this? Optical activity of a molecule is the ability of the molecule to change or to deviate the plane of plane polarized light. Now, that's very interesting. It's able to change the plane of plane polarized light. Now, what we have here is plane polarized light. Okay, now if we have a sample of an optically active molecule, okay, that molecule is a chiral molecule. So we have its sample in a tube. When this plane polarized light passes through this chiral molecule is able to change the plane of the plane polarized light. So at the end of the day, when this light passes through the chiral molecule, it may emanate in an orientation that looks somewhat like this. Okay, so that is optical activity, put very simply. The chiral molecules are able to change the orientation, they are able to change the plane of this plane polarized light. That is optical activity. Now, asymmetric centers are said to be chiral. Okay, but it's important for us when we get to see meso compounds, we get to see that meso compounds, although they have asymmetric centers, they are not chiral, and because of their achirality, they are not optically active. So there's a correlation between optical activity and chirality. So chiral molecules exhibit optical activity. Okay, so let's take note of that. Chiral molecules exhibit optical activity, and we just explained what optical activity is. Now let's take a look at some of these interesting pictures. Okay, this is a picture of what was explained earlier. So we have our natural light source right here. We have our natural light source that we can see right here. We can see the normal light. We can see that the rays oscillate in all directions in space. And then we can see our polarizer. Okay, this is the direction of propagation of the light. We can see that the plane polarized light, okay, because this filter has an axis of polarization that is vertical, so it only allows the vertically oriented rays to pass through, and we can see, of course, a plane polarized light. Okay, now that's our first picture. Now let's take a look at this. An achiral molecule is not optically active. Okay, by virtue of not being optically active, it means it's unable to change the plane of plane polarized light. Okay, So we can see a molecule, we can see a sample tube containing the achiral compound. We can see our polarizer has polarized the light, vertically oriented. It passes through our achiral compound. It comes out unchanged, okay, because the achiral compound is not optically active. Now this is very interesting. Let's take a look at this. Now we can see, as usual, we have our natural light source, we have our polarizer. It polarizes the light, and so now here we have this polarized, we have this plane polarized light. Now this plane polarized light passes through a sample tube that contains chiral compounds, and we can see that the emanating, while our plane polarized lights here are vertically oriented, we can see that after they pass through this chiral compound, this sample tube containing chiral compound, they emanate diagonally. Okay, so this chiral compound has been able to change the plane of the plane polarized light. Okay, so that's very interesting. That's the optical activity of chiral compounds. Okay, now let's take a look at this going further. Now for this video, won't be going in-depthly on how the specific rotation of plane polarized light is measured. Won't be going into details of that. However, it's important for us to take note of the fact that here's how specific rotation is measured. Okay, so first we have a polarization taking place here. Okay, we have our plane polarized light. Now in measuring the specific rotation, so we want to find the degree, the extent, the amount to which the plane polarized light is actually deviated from its original plane. Okay, that's what the specific rotation is. That's what the observed or specific rotation is. So what happens is that we have this plane polarized light, and then we place here an analyzer. This is very interesting. And so we let this light pass through. Notice that we do not have any chiral or achiral compound in between. So this rays of light actually pass through the analyzer. And right here we would have an observer. Okay, so we have an observer observing from here through the analyzer. The analyzer is another polarizer lens. Okay, just so we know. Now, this is very interesting. Okay, if we have our normal rays of light coming in this direction, okay, so they oscillate in all different directions in space. Now it passes through this polarizer, and the axis of polarization of this polarizer is vertical. So only the vertically oriented rays are allowed to pass through. So we have all of these vertically oriented rays moving through the polarizer. They are all moving through the polarizer. Very excited. Now, this is very interesting. If we have another polarizer whose axis of polarization is perpendicular to this, okay, so that means that the axis of polarization of this second polarizer would be horizontal, such that it's perpendicular to P1. So let's place P2 here. Okay, this is interesting. P2. Now we place P2 here, and its axis of polarization is horizontal, perpendicular to that of P1. Okay, now notice that P2 also acts as a filter, and it only allows rays of light that are oriented horizontally to pass through. Now take a look at this plane polarized light. There is no horizontally oriented ray of light. It means that no light would be allowed to pass through P2. On P2 there would be no light, and since there's no light, we would have darkness. Now this is very interesting. Let's take a look at this. When the light is made to pass through this analyzer, based on the orientation of the analyzer, light passes through. Okay, so the observer here is able to observe light passing through the analyzer. Okay, of course, remember that we cannot exactly see light and be able to tell that, oh well, that light is polarized and this light is not polarized. Polarization can only be measured by a polarimeter. Okay, we cannot detect or determine polarized or unpolarized light by mere seeing. Okay, so this observer is only able to tell that, okay, there's still light passing through the analyzer. Now the observer here continues to rotate the analyzer until no light passes through. Okay, now at the point where no light passes through, it means that the analyzer has an axis of polarization that is perpendicular to our initial polarizer P1. So that's what the observer does. Continue rotating the analyzer until there's no light, until there's total darkness at the point of the analyzer. Now, this analyzer has dials. Okay, it has dials that are able to measure the degree. Okay, now at the point where there is total darkness, that is marked as the point of zero rotation. Okay, it's marked as the zero rotation. It's like a case and control. The control is there's no chiral compound. Now let's take a look at the case. The case would be the would still have our analyzer here. Okay, we have the analyzer and then we have our observer here. So the achiral, or rather the chiral compound, has now been placed in position. Okay, the chiral compound has now been placed in position. Now, because we have changed the axis of the polarized light, some light is now able to pass through the analyzer. Okay, so the analyzer is still at the point of zero rotation, but because the chiral compound has changed the plane of the polarized light, some light is able to pass through the analyzer. Okay, now since light is able to pass through the analyzer, of course the observer is able to see that, well, there's no longer total darkness. So we have our point of zero rotation. Now the observer now rotates the analyzer once again until no light passes through the analyzer, and the observer takes note of the angle. Okay, remember we stated earlier that this analyzer has dials, so the observer takes note of the angle at which there is total darkness, and we call that angle alpha. Now alpha is the observed rotation. Okay, it's the observed rotation of the chiral compound. Now it's important for us to take note of the fact that this observed rotation is affected by various factors. It's affected by the wavelength. Okay, it's affected by the wavelength of the light passing through. Okay, it's affected by temperature. It's affected by the concentration of the chiral compound. So let's call that concentration of the chiral compound, or the number of chiral molecules within the sample, which is the concentration in essence. So it's affected by wavelength, it's affected by concentration, it's affected by temperature. It's also affected by the length of the sample tube. Very interesting. It's affected by all of these different factors. So it means that for observer A could observe the observer A could observe the rotation to be 23, okay, positive 23 for instance. And observer B, because they are working under different conditions of wavelength, temperature, concentration, observer B could observe theirs to be, take for instance, minus 20 or positive 25. Okay, because the observed rotation is affected by all of these factors. Now this brings us to the idea of specific rotation. Okay, now the specific rotation of a chiral compound is the degree of rotation of plane polarized light under specific conditions. So under specific conditions of temperature, under specific conditions of concentration, of length of sample tube, and of wavelength of the light. Now this is also very important for us to take note of. We're going back to physics because we're studying light here. Now when we studied physics and we studied light, we learned that white light is actually a combination of the 7 different lights. So we had the rainbow. Okay, we had red, orange, yellow, green, blue, indigo, violet, and all of that. And we're able to see this when we considered a property of diffraction. Okay, when the white light was made to pass through a prism, and then by diffraction it was divided into its various constituents. Okay, now when we consider this property of light, we learned that the red light has a different wavelength from the orange light. It has a different wavelength from the yellow light, from the green light, from the blue, from the indigo, from the violet. All of the different lights have different wavelengths, and we learned that it's as a result of the different wavelengths of these individual lights that causes for them to diffract when they pass through the prism. Now usually when we're considering the optical activity of chiral compounds, we make use of a monochromatic light. Monochromatic light meaning that the light has only one color. So we don't necessarily make use of the white light. If you're making use of the red light, make use of the red light. Making use of the yellow light, make use of the yellow light, because it has a specific wavelength. Okay, unlike the white light where we have all of these different combinations of light, or a polychromatic light in general, where we have this different combination of individual lights that have different wavelengths. That's just as an aside for us to take note of. Monochromatic light is preferable when considering the optical activity of these chiral compounds. Okay, now how are we able to calculate the specific rotation given the observed rotation? Okay, so we have our formula right here. The specific rotation is represented as alpha within the parentheses, these square brackets. We have T and lambda. Lambda represents wavelength and T represents temperature in degrees Celsius, to indicate that the specific rotation is measured at a specific wavelength and a specific temperature. Okay, so the specific rotation is equal to the observed rotation divided by the length of the sample tube and the concentration of the chiral compound. Okay, so the length of the sample tube is measured in decimeters, and the concentration of the chiral compound is measured in grams per milliliters. So it's important for us to take note of that. And of course the observed rotation is measured in degrees. Okay, so that's it for specific rotation. Okay, so we have considered optical activity, specific rotation. Let's take a brief look at enantiomeric excess. Now when we consider the fact that these optically active molecules are able to change the plane of plane polarized light, it's important for us to take note of the fact that while a particular molecule changes the plane of polarized light in a clockwise orientation, its mirror image would change the plane of the plane polarized light in an anti-clockwise orientation. Okay, so take for instance, we have the R of compound A. Okay, the R configuration of compound A is rotates the plane of plane polarized light in a clockwise direction. Well, it means that the S of this compound, given that it has one chiral center. So the S of this compound, which is the mirror image, would rotate in the anti-clockwise direction. So anti-clockwise is said to be level rotatory, and clockwise it's said to be dextro rotatory. Dextro for right, level for left. Okay, so it's important for us to take note of that. Now, level rotatory is given the notation negative. It's given the negative notation, and dextro rotatory is given the positive notation. Okay, now let's go back here. Now, it's important for us to take note of the fact that simply because a compound has an R configuration doesn't necessarily mean that it is dextro rotatory. In fact, by merely looking at a compound, you cannot determine whether such a compound is dextro rotatory or level rotatory. This is determined strictly experimentally. Okay, so R configuration is not synonymous to dextro rotatory, neither is S synonymous to level rotatory. The orientation or the rotation of a molecule or of a compound is determined experimentally. It cannot be determined by the orientation or the configuration about the asymmetric center. So a compound with an R configuration could indeed be dextro rotatory with the positive sign. The R, or a compound with an R configuration for another molecule, could be level rotatory. S could also be dextro, and S for another compound could be level. So R is not synonymous to dextro rotatory and S to level rotatory. It doesn't work that way. Dextro rotatory and level rotatory are determined strictly experimentally, so it's important for us to take note of that. However, if the R configuration of a particular molecule with one asymmetric center is dextro rotatory, the mirror image, which would be the S, would be level rotatory. Okay, so I hope we're able to understand that. Now, there's something very important for us to take note of, and is a racemic mixture. A racemic mixture contains 50% of the molecule with the R configuration and 50% with the S configuration. Now, this is very interesting. Of course, we've been considering compounds with one asymmetric center. Okay, now if, take for instance, the R has a level rotatory, the R is level rotatory, so it has a negative notation, okay, and the S happens to be positive, so it rotates plane polarized light clockwise while the R rotates anti-clockwise. Okay, now since we have 50% of both compounds, it means that when R rotates clockwise, or rather when R rotates anti-clockwise, S rotates clockwise to the same degree. So at the end of the day, there is no rotation, so the observed rotation would be 0. Okay, now this brings us to the idea of enantiomeric excesses. Now, before now, when enantiomers could not be separated, the samples of enantiomers were usually a mixture in varying proportions. So we could have 70%, or rather 75% R, and take for instance 25% S, or we could have 80% S and 20% R. Okay, this was how it was. We'd have mixtures of these enantiomers. Okay, now enantiomeric excess is used to determine to some degree the optical purity of a sample. Now, a sample is said to be optically pure when it contains 100% of the compound that has a specific configuration. So an optically pure compound would be 100% R or 100% S. Okay, it's optically pure. It doesn't contain some amount of R and some amount of S in the same sample. Okay, now what exactly is the enantiomeric excess? In a mixture where we have both the R and S configuration mixed together in a certain proportion, the enantiomeric excess tells us the amount to which a particular configuration is in excess. I'll repeat that. The enantiomeric excess tells us the amount to which a particular configuration of the compound is in excess. Okay, so take for instance, here we have 75% R and 25% S. Okay, now obviously we have more R than we have S. Okay, so 25% S. Now 25% R is able to cancel out 25% S. Okay, however, we have an excess of 50% R. Okay, so the enantiomeric excess of such a mixture would be 50%. Okay, so how exactly do we determine enantiomeric excess? Enantiomeric excess, represented as EE, is equal to the observed specific rotation divided by the specific rotation times 100%. Okay, this is how the enantiomeric excess is determined. Okay, now let's move very quickly to our next outline for the video. Let's take a look at enantiomers with more than one asymmetric center. Now, we'd be considering 3-chloro-2-butanol. Okay, this molecule has 2 asymmetric centers. Now, we could represent it like this: CH3. We have our carbon here, we have hydrogen, we have chlorine. On this side, we have hydrogen, we have the hydroxyl group, and then we have methyl. Okay, notice that this is an asymmetric center. It's attached to hydrogen, it's attached to methyl, it's attached to chlorine, and the entire of this group. Okay, and notice that this is also an asymmetric center: hydrogen, methyl, hydroxyl, and the entire of this group. Now let's take a look at how we name asymmetric centers. We're also going to be using the perspective formula or the perspective drawing. Okay, now we would pick our compound, okay, in this way. There is a carbon-carbon single bond. Now remember when we were considering the different classification of isomers and we considered conformational isomers, and we said these conformers could arise as a result of rotation about the carbon-carbon single bond. We also stated that there are two extremes. Okay, there's the extreme of the eclipse conformation and the staggered conformation. Now in the staggered conformation, the bonded groups are as far away from each other as possible, and in the eclipse they are as close as possible. Now we'll be taking a staggered conformation because a staggered conformation is more stable. The stability is determined by the amount of potential energy. So the less the potential energy, the higher the stability. But we won't be considering all of that in this video. So we'd be considering the staggered conformation. So the staggered conformation would look something like this. Okay, the dihedral angle is 180 degree. This is the staggered conformation. We know it's the staggered conformation because if we take a look at our Newman projection, if we have something like this and then we have something like this is a staggered conformation. Okay, an eclipse would look something like this. Eclipse would look something like this. We could see that the atoms are eclipsing one another. Okay, eclipse would look something like this. Now notice that for the vertical bond, that's this bond here represented in red, okay, it's oriented in an opposite direction from this bond. Okay, that's why we have represented this in this version, one going up and one going down. Okay, so we have our two solid lines. Now let's attach our wedges. So we have our dashed wedge and our solid wedge. We have here a dashed wedge and a solid wedge. As usual, the two solid lines must be adjacent and the two wedges must be adjacent. Okay, now let's take this to be carbon 1 and this to be carbon 2, and let's take this to be carbon 1 and this to be carbon 2. Now for ease, would be attaching the least priority group to the dashed wedge. Okay, the least priority group is obviously the hydrogen, so we'd attach our hydrogen here, and here would attach our hydrogen. Okay, now would attach our methyl here and our methyl here. Okay, for the staggered conformation. Okay, now we're left with just two bonds left, so would attach here the hydroxyl group and would attach here the chlorine. Okay, now having been given this a mirror image, okay, let's first of all determine the configuration of this compound. Now take note of the fact that we have two asymmetric centers, and having two asymmetric centers, it means that we'd have to determine the configuration of each of the asymmetric centers. Okay, we'd have to determine the configuration of each of the asymmetric centers. So let's do that. For ease, we already positioned the hydrogens to the hatched or the dashed wedges. Okay, now let's determine our priorities. This chlorine, this carbon 1, okay, so this is carbon 1, is attached to a carbon. Okay, it's attached to this carbon. We also have attached a hydrogen, is attached to chlorine, and it's attached to this carbon. In terms of priority, comparing each of the attached group, chlorine has the highest priority, so it takes the priority number 1. Hydrogen, of course, has the least priority. It takes priority number 4. Okay, so this is number 1 and then this is number 4. Now if we take a look at this carbon here, the methyl, and the carbon that is bonded here, we can see that we have this carbon, there's a tie. Okay, however, to break the tie, we need to consider the atoms that are directly attached to this group. Now this carbon, okay, this carbon right here is directly attached to a hydrogen, and a hydrogen. The carbon here, this carbon, is directly attached to an oxygen, okay, from the hydroxyl. It's directly attached to a carbon, and it's directly attached to a hydrogen. Now let's try to break the tie. We can see that this carbon wins over hydrogen, which we have here. So this is priority number 2 and this is priority number 3. Now going from 1 to 2 to 3, We have 1, 2, 3. Notice that we are going in an anti-clockwise direction. Okay, anti-clockwise direction, meaning that this is an S. Of course, our least priority is attached to the dashed wedge. Okay, so this has an S configuration. That's this carbon here. Now let's take a look at the configuration for the second asymmetric center. For the second asymmetric center, we know our least priority group to be hydrogen, and it's attached to the dashed wedge. Now directly attached to this carbon, to this asymmetric center, we have an oxygen, we have carbon, we also have this carbon right here, and then we have this carbon here. Okay, so 2 carbons, and then we have a hydrogen. Now oxygen wins. Oxygen is priority number 1. It has the highest atomic number, so this is priority number 1. Hydrogen definitely has priority number 4, lowest atomic number. Now these 2 carbons tie. Okay, so let's break the tie. The carbon here is attached to a hydrogen, hydrogen, and hydrogen. Well, the carbon here is attached to a chlorine, it's attached to a carbon, and it's attached to a hydrogen. So definitely the carbon here wins as priority number 2, and this is priority number 3. Now going from 1 to 2 to 3, let's take a look. From 1 to 2 to 3, we move also in an anti-clockwise direction. Okay, we move in an anti-clockwise direction, and since we move in an anti-clockwise direction, our least priority group is attached to the dashed wedge. This is an S. Okay, so both carbons have an S configuration. So here's what we have: carbon, carbon, they both have S configuration. So we have here staggered conformation, we have a dashed wedge, we have a solid wedge, we have a dashed wedge here, and we have a solid wedge here. Right here we have methyl, here we also have methyl, we have here hydrogen, we have here OH, we have here chlorine, and then we have here hydrogen. Okay, now let's take a look at this. Both of them have S configuration, S and S. Now let's take a mirror image of what we have here. The left becomes the right becomes the left. Okay, so we'd have our carbon, carbon, left becoming the right, would have our dashed wedge here. With the hydrogen, would have a solid wedge. With the OH, would have coming down right here, would have a methyl group CH3. On this side, the left becomes the right, would have methyl here, would have a dashed wedge with hydrogen, and a solid wedge with chlorine. Now let's take our configuration. Okay, for this carbon, we have the configuration to be, we already determined our priority, so this is priority number 4, this is priority number 1, this is priority number 2, and this is priority number 3. Okay, we're moving from 1 to 2 to 3, so we have something that looks like this. We're going in a clockwise direction. Okay, least priority is attached to a dashed wedge, so this is an R. Now let's take the priority for this. This is priority number 1, this is priority number 4, this is priority number 3, and then this is priority number 2. Okay, that's this carbon is priority number 2. Now going from 1 to 2 to 3, we're going in a clockwise direction. This is a clockwise direction. So this also is an R configuration. Notice that our molecule, our starting molecule, has the configuration SS, and this has the configuration RR. So they differ at both asymmetric centers. Their configuration differ at both asymmetric centers, and so these two molecules are enantiomers. Okay, this has an R and this has an R. These two molecules are enantiomers because they differ at both asymmetric center. Now let's change the configuration of just one asymmetric center. So given this, let's change the configuration of this asymmetric center. If we change the configuration of this asymmetric center, we're going to have another stereoisomer. So let's take a look at that. In order to change the configuration, we need to interchange any two groups. Okay, interchange any two groups. For ease, we'd interchange the methyl and the chlorine. Okay, so interchange methyl and chlorine. So we have a hydrogen here, we have a solid wedge with this, and then we have CH3. We have here, we're interchanging hydrogen, we're interchanging methyl and chlorine. So chlorine would be here, then of course we'd have a hydrogen, and now methyl takes the place of chlorine with this molecule. Okay, now let's take a look at this. Let's determine the configuration of this new molecule. This is methyl. Okay, this is configuration number 1 as we determined earlier. This is 2, this is 3. Notice that the configuration of this still remains an S. Okay, so this is 1, 2, 3. We're moving in a clockwise direction, so this has an R configuration. So this is an RS. Okay, this is an RS. Now let's create a mirror image of what we have here. Okay, so a mirror image of this particular molecule. So we have our mirror here. Let's divide this. These two are mirror images, non-superimposable mirror images. They are enantiomers. Okay, now let's create the mirror image of this. So left becomes right and right becomes left. Okay, so we'd have something that looks like this. We'd have hydrogen here. We have a H, OH. We have methyl. We have a carbon. We have Cl here. We have, this is CH3. Okay, we have here hydrogen and we have here CH3. Now let's determine the parity of this. The first carbon or the second. This is parity number 4. This is parity number 1. This is parity number 2, and this is parity number 3. Okay, now moving from 1 to 2 to 3, this has an R configuration. So this is an R. Okay, we're moving clockwise. So this is an R. Now let's take the configuration of this. This is parity number 1. This is parity number 2. This is parity number 4. And parity number 3. So from 1 to 2 to 3, we're moving in an anti-clockwise direction. So this is an S. Now notice that this is an R and this is an S. The carbon attached to the hydroxyl group is carbon number 2. The carbon attached to the chlorine is carbon number 3. So let's take out what we have so far. Let's call this 1. Let's call this 1. Okay, let's call this sample 2. We'll call this sample 3, and we'll call this sample 4. Now for sample 1, okay, for sample 1, carbon 2 has, remember, carbon attached to the OH, carbon 2 has an S configuration, and carbon 3 also has an S configuration. For sample 2, carbon 2 has an R configuration, and carbon 3 also has an R configuration. For sample 3, carbon 2 has an S configuration, and carbon 3 has an R configuration. Lastly, for sample 4, carbon 2 has an R configuration, and carbon 3 has an S configuration. Now notice that the compounds, rather compound 1 and 2 are enantiomers, and compound 3 and 4 are also enantiomers. Notice that they differ in configuration at the 2 asymmetric center. Okay, the 2 asymmetric centers are 2 and 3. Notice that 1 and 2 differ in configuration for both of the asymmetric centers. Notice also that the compound 3 and 4 differ in both asymmetric centers. Okay, the configuration differs for both of the asymmetric centers. So let's take this to a fresh page. Okay, now notice that 1 and 3 differ only at one asymmetric center, so they differ only at 3. However, for the second carbon, they have the same configuration. These two compounds are said to be diastemers. They are not mirror images, but they are not identical. Okay, I'll take that again. They are not mirror images, but they are not identical. They are said to be diastemers. Also notice that carbon or compound 2 and 4 have the same configuration at 2, but they differ only at one asymmetric center. They are also diastemers. They are not mirror images, but they are not identical. Okay? Also notice that 2 and 3, okay, that's 2 and 3, have the same configuration at the carbon 3, but different configuration at carbon 2. So 2 and 3 are also diastemers. They are not enantiomers, they are not mirror images, but they are not identical. Also notice lastly that 1 and 4 have the same configuration at carbon 3, but they differ at carbon 2. They are also diastemers. Okay, so the pair of enantiomers that we have here, we have 1 and 2 and 3 and 4. These are the enantiomers. Now for a given compound with n number of asymmetric centers, there are 2 raised to the power of n number of possible stereoisomers. So for the given compound, which was 3-chloro-2-butanol, we had 2 asymmetric centers. Okay, so n equals 2. The number of possible stereoisomers would be 2 raised to the power of 2, which is equal to 4. Of these 4 compounds formed, would have 2 pair of enantiomers, and then would have the diastemers, okay, amongst themselves. Now in naming these compounds, let's go back to what we have here. In naming diastemers, back to what we have here. This compound with the SS configuration 1 would be named with the configuration in parentheses. So it would be named as, so let's erase this so we can write down the name here. this would be named as, because it has the SS configuration, it would be named 2S 3S with the normal name 3-chloro-2-butanol. And the same applies for all of the 4 compounds. Going by our outline, so far we've been able to take a look at optical activity as well as isomers with more than one asymmetric centers, and also how to name them. We've been able to take a look at diastemers. Now very quickly, let's take a very brief look at meso compounds. Okay, a very brief look at meso compounds. Now this is the meso compound. Now this is the compound we'll be considering when we study, or for the study of meso compounds in this video. We have 2,3-dibromobutane. Okay, 2,3-dibromobutane. Here we have the methyl group, we have bromine, we have here hydrogen, we have here another methyl group, and we have here another bromine. Okay, now take a look at this. Before we go any further, take a look at this. Although this carbon and this carbon are indeed asymmetric centers, okay, this carbon is attached to a methyl, is attached to a bromine, it's attached to a hydrogen, and this entire group. So it's attached to 4 different groups. So it's actually an asymmetric center. However, there is a line of symmetry in this compound, as we'd go on to see. There is a line of symmetry. Okay, let's take a look at this. Let's try to draw the perspective formula. Okay, now remember we said that the number of possible stereoisomers for a given molecule with n number of asymmetric centers is 2 raised to the power of n. We have 2 asymmetric centers here, so we might make the assumption that, well, would have 4 possible stereoisomers. However, as we'd go on to see, we have only 3 possible stereoisomers, and it's because one of the stereoisomer is actually a meso compound. Okay, let's take a look at this. So we have a configuration that looks like this. We're taking the staggered conformation, CH3 CH3. Okay, and then for ease, hydrogen would be attached to the hatch. Okay, now this is methyl, this is a solid wedge rather, then we have a dash wedge, and then we have a solid wedge. Right here would have bromine, and right here would also have a bromine. Now take a look at this. Okay, let's determine the configuration. Wouldn't be taking a lot of time going over how the configuration is determined over again. It's quite clear. This is priority 1. Okay, this is priority 1, this is priority 2 right here, that's this carbon, and this is priority 3, and of course we have priority 4. So going from 1 2 3, 1 2 3. Notice that we move in an anti-clockwise direction, and our least priority is attached to a dash wedge. So this is an S. Okay, now take a look at this. This is our priority 1, this is priority 2, and then this is priority 3, this is priority 4. Let's move from 1 to 2 to 3. We move in an anti-clockwise direction. Okay, so this is also an S. So this compound has an S and an S configuration. So this is S and this is also S. Okay, now let's take a mirror image of this compound. Okay, so laterally invert, right? To laterally invert, take this, okay, the left becomes the right becomes the left. Okay, So right here we have methyl here, we have a hydrogen, we have bromine here. Right here we'd have the methyl here, would have a hydrogen here, and then we have bromine here. Okay, now let's take our priority. This is priority number 1, this is priority number 2, this is priority number 3. Going from 1 to 2 to 3, we have something that looks like this. So we're going in the clockwise direction, okay, which means that this has an R configuration. Let's take a look at this. This has priority number 1, priority number 2 is right here, priority number 3. Let's go from 1 to 2 to 3. We're moving in this direction, okay. Notice that we are going in a clockwise direction, okay. So this is also an R, right? Great. So this is R. Okay, so this has an R and an R configuration. They are actually mirror images. Now, they are mirror images because they differ at both asymmetric centers. Now, let's change the configuration of just one asymmetric center. Okay, let's change the configuration of just one asymmetric center. So we'd have something that looks like this. I'll draw this in the middle. Okay, it could be right here. Let's flip for ease. We'd change the position of methyl and bromine for this carbon. So bromine would come right here, taking the position of methyl, and then methyl would come down here to the solid wedge. And then of course we'd have our dashed wedge with hydrogen, would have another dashed wedge here with hydrogen, we'd have a solid wedge with bromine, and then here we have methyl. Now if we take our configuration, the configuration of this still remains the same as an S. However, we changed this, we flipped two groups, so the configuration would change, okay. And it's an R, but let's just determine it. This would change to an R, but let's determine that. So this is going to be priority 1, this is priority 2, this is priority 3. So going from 1 to 2 to 3, it's in the clockwise direction, so this is an R, okay. Now let's make a mirror image of what we have here. A mirror image of what we have would look something like this. Would have hydrogen here, would have methyl, or rather bromine, would have methyl, would have here bromine, would have hydrogen, and then would have methyl here. Now let's determine the configuration. To shorten the video, the configuration would be an R and an S. Notice that these two compounds are actually the same, okay, because they both have the RS configuration, so they are the same molecule. So in total we have only three stereoisomers for this compound. Also notice that because of the symmetry that exists, when the left side of this molecule rotates the plane of polarized light, take for instance in the clockwise direction, the right side will rotate the plane of the polarized light in the anti-clockwise direction to the same degree. So at the end of the day, there is no rotation. So although this compound in particular, although this compound has an asymmetric center, it's actually achiral, and so it exhibits no optical activity. It's called a meso compound. A meso compound. Okay, so the left is identical to the right and the right is identical to the left. There is a line of symmetry, although we have asymmetric centers. It's a meso compound, okay, and it doesn't exhibit optical activity, so it's good for us to take note of that. All right, so we've been able to consider all of this in this video. It has been a long video. If you liked this video, kindly give it a thumbs up. I hope we've been able to learn one or two new things from this video, hopefully. Thank you for watching this video to the end. Don't forget to subscribe. Bye.